So, welcome to another Math 1325 lecture. This is on implicit differentiation. So, what we've been doing so far is the functions you've been dealing with have been in this format, y equals f of x, where we only cared about one variable at a time. Well, what do we do if we have more than one variable? So for example, if I have a function that looks like this, x squared minus 2xy plus 3y squared minus 5, how could I do anything with this as far as derivatives because there's more than one variable? And this is what implicit differentiation is we say there's an implicit relation between the variables x and y. So how you do these is you differentiate both sides of the equation with respect to x, treating the y as a differentiable function of x. And how you do that is you take the normal derivatives, but if the variable's an x, you just take the derivative normally, you don't do anything differently. If the variable is not x, such as y, then you always put this dy dx after the derived y term. Collect all the terms with dy dx on one side of the equation, and then you solve for dy dx. So let's see an example. I have x squared plus y squared minus 25 equals 0. I want to find the derivative of this function and the slope of the graph at x equals 3. So we've been writing, a lot of times you'll see just y prime or f prime of x, but that means the same thing as the derivative of y with respect to x. So that means dy dx. So we differentiate both sides of the equation with respect to x. So x squared, I'm going to take the derivative of, y squared, take the derivative of, 25 and 0. And I treat y as a differentiable function of x, so wherever I see a y, I'll take the derivative and I'll put the dy dx after it. So the derivative of x squared with respect to x is 2x. The derivative of y squared is 2y, but because there's not an x there, we have to add this implicit part, the dy dx, and then the derivative of the constants are just 0. So now I want to collect the terms with dy dx on one side, because that's what I'm solving for, is I'm solving for dy dx. So I subtracted 2x on both sides. I divided both sides by 2y, and I can also divide both sides out by 2. So I get dy dx equals negative x over y. All right, so we found dy dx. I want to find the slope of the graph at x equals 3, so I can plug in x equals 3. Well, how could we find y? Well, remember we had an original equation. We could go back to our original equation, plug in 3 for x, and then we could solve this for y. And so I go through all the steps, 9 minus 25, negative 16. I throw the 16 to the other side. And then I square root both sides. Remember, when you square root, you're doing the plus and minus, because positive 4 times positive 4 will give you 16, and so will negative 4 times negative 4. So you get two answers here. First, let's look at, we have our dy dx, where our y, let's look at this where our where our y is going to be the positive 4, and then we'll plug in the negative 4. So what happens here is we had two dy dx's. We have the slope at x equals 3 and 4 is this negative 3/4. We have the slope at 3 and negative 4 is 3/4. So we have two different slopes. Well, let's find the tangent lines. How do you find the tangent lines? Hopefully you've done this enough times that you remember it's the y minus y1 equals m times x minus x1. So I'll do it for the first point, the 3, 4. I'll also do it for the other point, 3, -4. So both of these are just my y minus y1 equals m times x minus x1. And then I can plot these to see, because hopefully you're sitting there going, why would there be two slopes? Well, remember when we did the plus and minus, we got two y values here. And if you recognize this equation, it's the equation of a circle. X squared plus y squared equals 25 is the equation of a circle. If I square root the 25, I get 5, and that's my radius. And that's why you can see we have two different slopes here. So this shows where you could have a function that you could have one x value in this case and have two different y values, and you're interested in both of these y values. In this case, their slope or the tangent lines. So circles are great for examples because that was easy to see why you might have two different slopes. But let's look at an actual business application. So I have a demand equation here. I want to find the rate of change of price with respect to demand. Remember, my x is demand, by differentiating explicitly. So I take this equation, and every one of these, I take the derivative of the price with respect to x. Every single term. If the term does not have an x, then I have to follow it up with the dp dx after it. So the derivative of x is just 1. The derivative of p to the fourth is 4p to the third, and I have to follow it with the dp dx because there is no x variable. The derivative of 5p squared, well, 2 times 5 is 10. Subtract 1 becomes p. Again, no x, so I put my implicit part, my dp dx. And of course, the derivative of 300 is a constant. And so now I want to solve this for dp dx. So probably what I would do is I would factor out a dp dx, and then I could divide both sides by this 4p cubed minus 10p. And what this gives me is this is a rate, this is a derivative, the rate of change of price with respect to demand.